Now we will discuss another problem which will be dealing with the similar effects, which are the first law, second law, and third law of motion, and also will be dealing with the normal forces, contact forces as well. So we have another problem. The problem second. Here we have we have a particle inside a vertical cone. Here also frictional force is absent, so we have a cone like this. Okay, we have a cone like this, and the particle is moving inside it. This is a particle moving inside this cone in a circle. Since if it is set in motion inside this cone, it will be moving with the circular motion like this. This will be a circular motion. This will be a circular path followed by this particle inside this cone, having some radius of this circle, not the cone, radius of this circle, which is exhibited by this particle. Okay, so this will be, say, the radius of this path is r. And another thing you have to keep in mind, the half angle of the cone, that is slant height here, is slant angle here. This angle is theta, half angle. Keep that in mind. This half angle is theta, and the mass of the body, this mass of the particle here is m, is moving in the circular motion inside a cone which is frictionless. This is the problem. A frictionless cone, a body moving inside it in a circular motion, frictionless, with mass m and and velocity of that very particle, velocity of particle is v. Okay, so we have to find the radius of circular path in which the particle is set in motion, circular path. So we have to find this r. R is unknown here, so we have to find the circular path radius. Okay, so how to find out that? Keep this diagram in mind. We have particle moving along a circular path. The conical half angle is theta, velocity is v, and the mass is m. So how to determine this sort of problem? So keep this here in mind that body surface is frictionless, so no contribution from frictional force. The only force which will be exerted onto this body, m, will be either contact force between the walls of the cone and the body, and the downward force, which will be the weight. So draw the free diagram. First of all, draw the free diagram. Draw the free diagram. Okay, how that is drawn? I will say this is the wall of the container, that is the conical shape which I have shown you here. This is the wall of the cone. Onto it, the body m is here. It is moving in circular motion. It is set in circular motion like this. Circular path is like this. Okay, this is the circular path. The different kinds of forces which are acting over this, and keep it in mind, this is the half angle of the cone which I have shown earlier. This is the theta. Okay, first and foremost, to draw the free diagram as follows. The downward force will be mg, because the mass of the body is m, so the downward force with the weight of the body will be mg. Another thing, the normal force will be perpendicular to this surface, because normal force is always normal, meaning the perpendicular to the surface, and that will be given like this. This will be the perpendicular n. So it will be perpendicular to the surface of the cone. Now only these two forces are acting on the body. No frictional force, no external force. All external forces are absent. All external forces are absent, that is zero. Only these two forces are acting. So since the body is set in motion in the prior time and now no force is acting on it, only the downward force due to the body itself, that is the gravitational force caused by the gravitational force, that is the weight of the body, and the normal force due to the contact between the body and the surface. So we have to divide it into the component form because we have to see which component contributes to the motion along the circular path. And to set a body in circular path, we need a central force, that is the centripetal force. Centripetal force is we can say is required for a body to set it in motion, for a body to remain in circular path. Okay, so we have to find that very circular motion, that very centripetal force. Okay, and that very centripetal force will be towards the center of the circular path, not the center of this cone, but the center, even though that will be the center of the cone as well at that plane. Okay, so that will be center of the circular path. So divide these very forces in the component form. We will get it as follows. This very thing, normal force, draw this very mg, it will be divided in, first and foremost, this is the theta, this is the slant height, this is the direct height of the cone, and this is the downward force mg. These two lines are parallel to each other, and this very is intersecting these two. And we know from the law of intersection of the two lines, if two lines are drawn parallel and if two lines are parallel and intersected by another line, then this very angle and this very angle are equal. This very angle and this very angle, these two are equal because these are interior angles between the parallel lines. Okay, similarly this very angle and this very angle is equal. Fine. So here this very angle and this very angle will be same from the law of intersection of the lines. So this will be theta. This is a mathematical formulation. You have already seen these very things in the earlier classes as well. So this very angle is theta, this very angle is theta. So here the component will be this very thing, and this will be the cosine component of mass times gravity. So this will be the mass times gravity cosine component because it is along the component of the theta. Okay, similarly along the perpendicular, it will be mass times gravity into the sine component because it is the perpendicular to this very base. Okay, this will be the cosine component. Similar, you have already seen it. If we have two perpendiculars and a vector in between like this is the vector v, and this is making an angle theta with this axis, say this x component is y. Okay, then along this very axis, the projection of the vector will be v cosine of theta. Okay, and along y-axis it will be v sine of theta, the projection of this very thing. So this will be the v sine of theta, and this will be the v cosine of theta. Similarly here, mg sine of theta along this very axis, mg cosine of theta along this very axis. Similarly for n, we have draw the perpendicular upon this. So here the perpendicular on this is this line, and the perpendicular on this very thing is this line. So the angle between these two is also same as that of theta, because we know that, note it down, angle between two lines is equal to the angle between their respective respective perpendicular lines. So that means if we have two lines here, one is like this and another is like this, if this is the angle theta between these two lines, then the perpendiculars to these two lines, they will also meet at some angle, and that angle will be similar to that of the theta. That means if we draw this very if we draw a line perpendicular to this very line, say like this is perpendicular to this on here, and a perpendicular to this will be perpendicular to this. Okay, then the angle this very will be theta. Similarly, this will be also theta. Fine. So this will be the angle similar to that of the theta, because these are perpendiculars to these original lines. Similarly here,